In the next section of chapter 14, we're looking at some vocabulary terms to learn qualitative terms associated with the concentration of a solution. Remember, qualitative refers to a quality or to a characteristic rather than having a number associated with it, which would be quantitative. So we are looking at only descriptive terms associated with the concentration of a solution. So a solution is made of two different parts. We have the solute and the solvent. Together, those form the solution. A commonly accepted definition of solute is that it's something that gets dissolved. However, this creates issues because it really only applies to solid liquid solutions. But a solution is any homogeneous mixture of matter, which means we can have gas-gas solutions, we can have solid-solid solutions, we can have liquid-liquid solutions, which would make determining which one gets dissolved rather difficult. So instead, we use a slightly different definition. And this definition of a solute is the substance present in the smallest amount. So this really serves to correct for the fact that we don't just have solid liquid solutions. In a solvent, normally we would think of this as the opposite, the one that dissolves another substance. But remember, this definition doesn't apply to all of the different types of solutions. So instead, we say that it's the substance present in the largest amount. So if we have two liquids that are mixing together, then we can say that the solvent is then whichever we have more of. The term saturated, I think of the term saturated like a wet towel is saturated, and a dripping wet towel is one that is saturated because it cannot hold any more liquid. So in solutions, it doesn't really mean much different. A solution that contains as much solute as will dissolve at that temperature, and at that temperature becomes more important going forward. But right now you can think of it like a wet sponge. If you can hold the sponge there even without squeezing it and there's water dripping from it, that is what's known as a saturated substance or saturated solution. Unsaturated is just how it sounds. It means it can still hold more. It's a solution that can still hold more solute. Like a damp towel or a partially dry towel is unsaturated because it can still hold more liquid. Solution, again, is no different. It's a solution that can still hold more solute. So think of it like dissolving salt in water and still being able to add more salt. So this dry sponge is an example of something that would then be unsaturated because obviously it can hold more liquid. Supersaturated. So if saturated means it can hold the maximum amount of solute, how can we have something that is supersaturated? Supersaturated means that it can hold more solute, but that higher temperature piece is what's required to drive more solute into the solution. So we can see in this first picture, we have a room temperature solution of, say, salt and water. And in this case, we have a saturated solution, meaning no more salt will dissolve. I've poured as much salt as I can into that solution. Any extra salt that I add will collect on the bottom. That's what a saturated solution means. It can't hold any more solute. If I heat up then this saturated solution, what I'm allowing this to do is essentially make more room for more solute particles. So by letting those water molecules spread apart, they can hold more solute, more salt, more sugar, whatever it is that I'm driving into this solution. And then as I cool this solution back down, we now have more solute particles than we could originally hold at room temperature. This process is most often used for making things like rock candy. So with rock candy, you put a lot of sugar in water, and then you heat it up to allow that sugar to dissolve. And then at the point when you have too much solute in that solution, you have a supersaturated solution. That supersaturated solution is very unstable. All of that solute in the solution wants to fall out. So with a little bit of nudging, either from what we call a seed crystal, which just means you take a little crystal of sugar and you put it in this solution. Normally it's on, we see it maybe on a string. We do this with a paper clip, and the paper clip holds a string down on the inside. And then we coat that string in sugar to allow those solute particles something to grab onto. So this is why commonly you see rock candy on strings. You can also do it just using a skewer. So if you place that skewer in the solution of rock candy and again put some seed crystals in there, then you can have this rock candy growing on this bamboo skewer normally. So all it takes is a little bit of nudging from that seed crystal, and then if you're at room temperature, you're allowing that solution to become unstable, and all of those solute particles will then grab onto those seed crystals and just continue to grow, which is why you see those very large crystals of rock candy rather than small crystals of sugar like you would normally see. The crystal growth process is slow, so that's what makes the crystals bigger. Saturated versus unsaturated fatty acids. So we've heard these terms before, most often when referring to things like margarine or butter, but the term comes from what's called a site of unsaturation. So you can see this saturated fat, much like referring to a solution, a saturated solution means it's as much solute as it can hold. In the case of a saturated fatty acid, I have as many possible hydrogens as this compound can hold. Notice there is no more room for any sort of hydrogen atoms attached to the rest of these carbon. It's completely saturated. In an unsaturated fatty acid, we have a double bond, and that double bond is what's called a site of unsaturation. So normally what I would see is these two hydrogen down here, but what's happened is those have been removed. And if those get removed, then we develop this double bond or this site of unsaturation. If I see one double bond, that's a monounsaturated fatty acid. If I see more than one, that's a polyunsaturated fatty acid. So the prefix refers to how many there are. Mono is one, poly means many. So this plays directly into what we know about saturated versus unsaturated fats in nutrition. So if we're looking at saturated fats, those are most commonly found in processed foods, the more preserved foods, the ones that aren't going to go bad, because they're more likely to be solid at room temperature than unsaturated fats are. Now we've heard the term dilute versus concentrated before. Most often we hear the term concentrated when we're talking about things like color. Saturation also refers to color. Those of you that are familiar with art may have heard that term used in that way before. And if you're looking at saturated color or concentrated color, you're talking about a more vibrant color. You're talking about one that has more of those color particles in it. So we have to remember that the term dilute is a relative term. We can't talk about something that's dilute without talking about it being related to something that is more concentrated. So we can only use them in reference to each other. So we see this picture. Picture this as a cup of water with some Kool-Aid or some red food coloring put in it. This is our dilute sample right here, because the water would end up being the solvent. The Kool-Aid or the red food coloring would be our solute. So whichever one has the smallest amount of solute would be our dilute sample. So the opposite of dilute is then concentrated. It's a relatively large amount of solute in that same glass of water. So again, if I only was looking at maybe just this one right here, then what I would be seeing is just a red substance. I wouldn't know what was in it. I would have to compare that to the spectrum of concentrations to be able to determine if it was concentrated or dilute. If I was just looking at that one on the left, I wouldn't know if there was something that was more concentrated or less concentrated. But if I'm looking at the whole spectrum, I would then be able to tell that this is our dilute sample, and then this would be the more concentrated sample. And we can go every step along the way. This is the most dilute right here. And then this is in order of most dilute to most concentrated. It would fall just on this spectrum right here for being the most concentrated. But remember, it's a relative term, so you can only use the terms concentrated and dilute relative to each other. Just a small note to not confuse the term concentration with strength. So concentration specifically refers to the amount of solute that's there, either a lot being concentrated or little being dilute. Strength refers to an inherent property of whatever substances you're talking about. Strong coffee refers to the roast of the coffee, not necessarily how much coffee is in an amount of water. So just be very careful with the difference between concentration and strength because they are two different things. In section 14.3, we're going to look into the more quantitative aspect of concentration. So our aim for this section is to understand the concentration term mass percent and to learn how to calculate it. Now, we've seen this a little bit before when we've looked at things like percent composition. It's the same concept. So remember, anytime we're looking at a percent, we're always looking at the part over the whole. And here we're talking about a solution. So mass percent equals the part, which is the mass of our solute, versus the whole, which is the mass of the solution. So remember, the solution is made up of the solute plus the solvent. So what we want to focus on here is just the solute. And then if we multiply that by 100, that gives us a percent. So remember, mass is in units of grams. So we're looking at grams of solute. And then solution, again, is solute plus solvent. So we have to add both of those together to be able to determine the mass percent. If we're given those, we may just be given mass of solution, but we also may be given solute and solvent and then have to add those together. And then, of course, multiplying by 100. Do not forget to multiply it by 100. A lot of people do, and then that answer numerically ends up being wrong because you're just expressing it as a fraction rather than as a percent. So your sample problem. A solution is prepared by mixing 1.00 grams of ethanol, which is C2H5OH, with 100.0 grams of water. Calculate the mass percent of ethanol in this solution. So the first step is going to be to write down your equation before you plug anything in. The mass percent of ethanol is equal to the mass of ethanol divided by the mass of the solution. So grams of ethanol divided by grams of ethanol plus grams of water. So remember, we want the total mass of the solution down on the bottom. And then we have to multiply by 100. So what is our mass of ethanol? We were given 1 gram of ethanol in the problem. We're going to use that 1 gram again when we combine that with the mass of water to form the mass of solution. So down here we use that same 1 gram of ethanol. This time we're adding it to 100.0 grams of water. So to simplify this further, we get 1 gram of ethanol divided by 101.0 grams of solution times 100, and this gives us 0.9900990%. And of course, if we're observing sig figs, we want to just look at 3 sig figs in this problem, so it would be 0.990% ethanol. Another problem. Cow's milk contains 4.5% by mass lactose, which is C12H22O11. Calculate the mass of lactose in 175 grams of milk. Same equation, we're going to use it slightly differently here though. This time we're starting with the mass percent because they gave us the mass percent in the problem, which was 4.5%. 4.5% is equal to the mass of my solute, which in this case is lactose, because we're looking at the mass of lactose in milk. Milk would then be the solution. So we're trying to find this x grams of lactose divided by 175 grams of milk. This part gets just a little bit tricky because we have to remember that we had to multiply it by 100 to turn it into a percent in the first place. So the very first thing we have to do is to divide both sides by 100. And if we do that, we turn that percentage back into a decimal. So we have 0.045 equals x divided by 175. That part did not change. And the last part, we've already canceled out this 100, so we're not worried about that anymore. The very last part is multiplying both sides by 175. And if we do that, we get 175 times 0.045 equals x. A quick calculation gives us 7.9 grams. Notice this observes sig figs because we had 2 sig figs in 4.5%. And we have to include that final label, which would be lactose. So your final answer here would be 7.9 grams of lactose.